So project is parallelizing programs with multicore error and malfunction.
David Liao.
And Ryan Moore.
So just an outline. First off, we're going to give you a brief introduction as to what our project is investigating. We'll provide you with some background information, go through our procedures, and provide results, conclusions, and
All right, so in computing, we now have processors that are very fast. They can run at 2.4 gigahertz speed, which is eons ahead of what we've had in the past. But we still have a problem that programs run very slowly often. Now, one of the reasons for this is that we are running much more complex computations on our machines now. That does contribute. The biggest contributor is the memory access bottleneck. When we're working with large sets of data, the access of the processor to memory is still very slow. And so that is really the number one slowing thing for our programs. And any software can benefit from optimizing this and reducing this lag. And so if you have scientific analyzing software, any software you have, graphics rendering, it could benefit from this.
So just a brief background on the CPU architecture. CPU stands for the Central Processing Unit. And nowadays, most CPUs are multi-core. Within each core, there is usually 2 threads. Each thread is a single unit that's able to carry out a series of operations. The most relevant to our project is the memory hierarchy. This includes caches, which there are 3 levels, generally level 1, level 2, and level 3. As you go up in levels, the size increases and the latency decreases, which means they run slower. So the most important thing about caches is that they speed up runtime by allowing quick fetching of data. So when data is generally used, it's stored based on 2 principles: temporal locality and physical locality. Physical locality. So temporal locality is the idea that once you use data in the near future, you plan to use it again. Physical locality is once you use data, you want to take the data around and store in the cache in hopes that you'll use the data around it as well. So when you're successfully storing something and the CPU successfully retrieves it, this is known as a hit, and it greatly speeds up runtime. However, if you miss it, you'll have to go up to a higher level, such as being a ring or a higher level of cache, to retrieve that data. And we'll be talking about performance advantages.
Okay, so the question is for our project, how can we quantify the effects of our program on the caches? And what we can do, we can use what are known as performance counters. So these are specialized registers within the processor that we can configure to monitor certain types of events. So what we chose to do is we chose to monitor our cache miss ratio. So we would see how many misses we had in the cache as a percentage, and then we could quantitatively determine how well our program used the cache.
All right, so the basis for our project is multi-threading. Now, modern processors have the ability to run multiple operations simultaneously, parallel. So you don't have to run one operation after another. You can instantiate multiple threads, which are individual units, and they will all compute data simultaneously, speeding up the program. Now, a very important concept in multi-threading, also parallelization, is the idea of resource sharing. Now, when you have multiple threads accessing the same resource, or a variable or some data, you can run into the problem where if multiple threads try and access the data at the same time. And if this happens, the data can get garbled, it can get modified while another one is reading it, so it causes a lot of problems. So the solution to this is something called mutual exclusion, now also called mutex. Now mutex is essentially an agreement between threads not to modify data while another thread is reading it. And so we have this idea of a mutex lock. And what happens is one thread that needs to work with the data will lock the mutex, meaning that it's the only one that can work on it. It will do whatever it needs to do with it, and then when it's done, it will unlock it, allowing other threads in this one to work with the data. And so this is how we prevent collisions of multiple threads trying to access the same data. And so pthreads is the name of a POSIX compliant API for parallel programming in C. And now there are many other APIs out there, but pthreads is a nice standard one that we decided to use, and we wrote all the programs for this project in the C programming language. And matrix multiplication is the program which we decided to parallelize. Now, just a quick overview, it's an important mathematical operation. If you have 2 matrices and you're trying to compute the product of the 2 matrices, you traverse the row in the first matrix and the column in the second, multiplying pairs of elements and then summing them all up. And that's how you create you multiply two matrices. So this, if you have two matrices of size n by n, multiplying them will take n cubed steps, meaning that as you increase the size of the matrices, you increase the speed of the runtime cubically. And so this gets pretty slow, and so we wanted to see if we could improve the speed at which we multiply matrices.
Procedures that we did that we ran through, the test that we ran through. So first we want to test how the program ran in serial. So we only used this on one thread, and as Ryan had said, it ran it over n cubed time. What we did was we computed every single element in the resulting matrix iteratively. Following that, we decided to test the program in parallel. So then what we did was we assigned rows to individual threads, and then we computed them that way. And following that, we did the lock n procedure, which instead of assigning a single row to a single thread, we assigned multiple blocks of rows to threads. And what we wanted to see was whether or not we could decrease the communication between threads to increase runtime, decrease runtime. And we wanted to see if the n, which stood for the number of rows that we assigned, actually mattered. So we compared that to block random, which meant that we assigned a random number between 1 and n to threads.
Alright, so there's another optimization that we implemented that isn't strictly parallelization, but it's very important because it emphasizes the effect of cache misses on runtime performance. And so you have to know you have to understand the way the matrix is stored in memory is that it was originally by row. And so you have each row would be contiguous in the array that it's stored in. Now this works very well for the first matrix because when multiplying you traverse across the row. And so that conforms to the idea of the physical locality, meaning that we use this data just now, so we're probably going to use the data right next to it soon. Now that works for the first matrix, not the second matrix, because in the second matrix it's traversed by the column. So what we did to make physical locality effective in the second matrix is we transposed it in memory and essentially stored it by columns. This way we're traversing directly across the array, meaning we had less cache misses, and so hopefully this would improve our performance.
So most of the data that we generated was done through scripts that we wrote. So the scripts that we wrote were generally in Bash, which is Unix-based and is a shell scripting language. Our programs that we wrote in C, different variables that we modulated through these shell scripts. Some modulated variables that we wanted to test were thread sizes, matrix sizes, and n-size blocks, which refer to the assignment of rows to threads. And finally, we recorded the data and outputted it into comma-separated value files, CSV files, and which were imported into MATLAB to generate graphs.
All right, so now for our results. So this first graph shows the running time of a simple serial matrix multiplication program versus the matrix size in the rows. This graph shows us is that the runtime does increase cubically. This is a third order cubic fit to the data, and it fits so that's a cubic increase in the runtime. This helps show that the algorithm does perform as we expected it to, and the program does work as we expected. This next graph shows the speed up versus number of threads for a matrix that was about 2,000 elements on a side. You can see here for one thread, we actually have a less than 1x speed up because there's a bunch of overhead involved in creating a thread. And you can see that our speed up increases up until about 5.5 to 6 times, which it plateaus at about 16 threads. And what we hypothesized here was that the server that we tested this on had 16 physical cores and 32 threads that it could execute at once. However, each of these threads, each core has a certain amount of memory bandwidth, but the threads don't have more. So you can see here, once we hit the maximum amount of memory bandwidth, there's no real advantage to adding more threads. It's not going to speed it up any further. So this shows that this is a really memory-intensive application. Then the final thing, it's the lock n versus lock random. So as mentioned earlier, lock n locks a block of n rows at a time, whereas lock random locks 1 through n rows at a time randomly. And you can see here there's no real difference between the two. They're running about the same time. So then our next question was, how does the runtime change as we change n? So this again, matrix was 2,000 elements on a side, multiplied. And we have here the value of n changing and the running time in seconds, and both scales are logarithmic. So you can see here, as we increase the value of n, so the number of rows that we lock at one time, we have almost no change in the running time. Each of these different markers is a different number of threads. So for any number of threads, there's almost no change in the running time as we change n. And then finally, we wanted to examine how transposing the matrix in memory affected our running time. So this graph shows the number of threads and the running time in seconds, and you can see runtime does decrease with increasing threads. You can also see that for all the thread values that we tested, transposing the matrix got us a good performance gain. You can see here we have about 15 seconds for a transposed matrix versus more than 20 for a non-transposed matrix. And we wanted to see how that was affected by cache performance and cache misses. So here we have the L3 cache miss fraction for each of these programs, each of these tests. And what this is we counted the number of times we attempted to access this cache, the number of times we missed the cache, and we just figured out what percentage of attempts missed. So you can see here that for 8 threads, in the transposed version, about 1 in 5 accesses missed, whereas in the non-transposed version, it was 3 in 5, or 60% of the accesses missed. You can see there's a significant difference in the performance of the program, and especially the cache performance for differing transposed versus non-transposed.
Right, so let's just go back to what we were going to do. We wanted to investigate the architecture of the CPU and the memory hierarchy just to understand better how we can improve the performance of the program. One, we created the serial program for matrix multiplication to serve as a baseline, and to also show that yes, it does increase with in n squared, n cubed time cubically. So we want to parallelize the program and have some sort of performance increase, and that includes the matrix transposition. We wanted to quantify any performance increase we saw with the runtime, with the actual runtime, and with the performance counters. And so we conclude that yes, the serial program does slow cubically, and also the parallel program does also slow cubically, because we are changing we have a multiplier, so we're not changing the rate at which the speed slows down, but we are changing the actual speeds that we get. We achieved up to a 6x speed up in certain cases, mostly with larger matrices and with more threads. And we learned that other optimizations, such as the matrix transposition, are very important because the underlying cause of slowness is cache misses. And we learned that there's still a limit to the performance boost that parallelization can bring, and this is due to a number of limiting factors. Most importantly, the still slow memory access speeds and the size of the cache that you have in your processor.
Finally, we would like to extend our thanks to our professor, Professor Abhishek Parasharshi, our RTA, Brian Belting, our director, Ali Rosen, our assistant director, John Patrick Anton, Rutgers University Department of Computer Science for providing us with the server just for Dix. Special thanks to our sponsors, Rutgers University, the state of New Jersey, Morgan Stanley, New Jersey Resources, South Jersey Industries, TCG, and finally the GSET alumni community. Thank you.
I have 2 questions. One, can you go back to the slide of the in-lock versus random lock?
Yes.
So what is your explanation for why both gave roughly the same performance?
All right. Well, the reason we thought they would give different performance was because the way we locked the threads was with a mutex, some mutual exclusion. And what we thought was that the threads would all try and access the mutex at the same time with lock n, and that would give us lower performance. The reason that they don't give any different performance, first off, each row is a significant block of computation. So there's a very course, already. And also, depending how randomly the threads are scheduled, it can be scheduled so that they don't all try and access the same mutex at the same time. And then lock random wouldn't give us much of an advantage.
Okay. Could you go to several slides forward, the L3 cache miss rate? Yeah, miss fraction. So is there a corresponding slide that shows me the actual performance improvement or degradation in those two scenarios?
Yeah, that's the previous slide here.
Okay.
So this shows on the y-axis how long it took to run and how many threads we had.
Okay, so that eight thread one at the end is talking about 3 versus, say, 6 seconds, right? Am I reading that correctly?
Yeah, it looks to be about 3 versus 6.
3 versus 6. Okay, so then go one slide forward. And so you're saying that that's attributable to changing the miss fraction from 0.2 to 0.6.
Yeah, so what we found was that our first version was non-transposed, and then once we transposed it, we managed to decrease the number of cache misses. That was really the only thing we changed in that program. It still did all the same computations, still did them in the same order, just arranged things in memory differently. So there's no real other explanation for the decrease in runtime except for us changing the memory organization of the data.
So which cache level is the biggest limit? I mean, if you had fixed number of dollars or capacity to improve level 1, 2, or 3, where would you put your money?
Well, it'd be probably best to spread it across the levels because each level is a different size. They're also a different speed. So level 1 is the smallest and fastest, whereas level 3 is the largest and slowest. So level 1 is good for storing data that will be used a lot. And level 3 is used for storing data that will be used slightly less, but still often. So if you have just one really large level 3 cache, every miss will be slow. Whereas if you try and increase the size of the level 1 cache, you'll end up missing a lot more, and then you won't have a level 3 cache to go to get the data from.
All right, if there's no more questions, one more round of applause, please.